For the last few years, the standard approach to AI has been straightforward. Build one massive model and throw every problem at it. If you need code written, a database searched, or a math problem solved, you send it to a generalist like GPT-5 and expect it to process every single task in the workflow. Relying on a single massive system for everything is incredibly expensive. Running hundreds of billions of parameters just to execute a simple web search or trigger an API burns through compute budgets. Worse, asking a language model to handle strict logic tasks without external calculators or interpreters routinely leads to hallucinations. You might think the solution is to prompt that large model to act as a manager, telling it to hand off tasks to smaller, specialized tools. But when researchers tested this, they found a persistent flaw called self-enhancement bias. If you ask GPT-5 to route tasks efficiently, it overwhelmingly ignores third-party tools and defaults to its own mini version, regardless of whether it's the best or cheapest option for the job. Prompting a massive AI to manage tools triggers this self-enhancement bias. Because the model favors its own developmental variance over actual cost or utility, you cannot rely on an off-the-shelf system to act as a manager. True orchestration requires a dedicated, purpose-built routing model that is specifically trained to weigh the exact cost, latency, and accuracy of every available tool. This requires moving away from the single-brain approach. We are shifting toward a corporate-style structure, where a specialized, lightweight orchestrator model sits at the center, dynamically delegating tasks to a vast array of specialized workers. Training that dedicated orchestrator requires an enormous amount of data showing perfect tool use. This creates a severe bottleneck. While we have petabytes of human text on the internet to train language models, we have almost zero recorded logs of the optimal thought process and API sequences humans use when solving complex problems. Because human tool use data doesn't exist at scale, researchers have to manufacture it. They build virtual environments that generate their own training data through a closed-loop generation and verification process. Starting with a broad domain, an AI generates a complete virtual database schema, populates it with thousands of fake, consistent rows, and writes the Python functions needed to query it. Once the virtual world exists, a teacher model looks at the database and asks a specific question. Because the system created the database, it can execute the query itself to find the exact answer. This automatic verification creates a perfect ground truth label, linking the original question to the precise sequence of tool calls needed to solve it. To ensure quality, the system generates 8 different pathways to solve that one problem. If none work, it is discarded. If multiple paths succeed, the system filters the results using a pass-at-8 criteria, keeping only the single most efficient, successful trajectory to use as a positive reinforcement sample. Manufacturing verifiable data this way solves the volume problem, but it introduces synthetic bias. The resulting orchestrator becomes highly efficient at executing paths, but its core reasoning capabilities are permanently capped by the intelligence of the teacher model used to generate the environment in the first place. Once the synthetic data is manufactured, the focus shifts to the actual training. Researchers use reinforcement learning to teach an 8 billion parameter model exactly how to sequence those tool calls. This chart shows the loss landscape during reinforcement learning. It highlights a massive hurdle called the variance problem. Because the gradient estimates are noisy, a single lucky rollout where the model accidentally guesses the right sequence can trigger a massive weight update. That sudden shift causes catastrophic forgetting, where the model breaks its own language circuits just to maximize a reward. To stabilize this erratic training process, you have to run massive batch sizes. Training a reinforcement learning orchestrator requires a dedicated cluster of 16 H100 GPUs, not to speed up the process, but as a strict mathematical necessity for variance reduction. By averaging hundreds of trajectories simultaneously, the system filters out the noise and finds a stable, reliable direction for the model to improve. Because these trajectories vary wildly in length, from a 500-token web search to a 12,000-token debugging loop, engineers use sequence packing. They concatenate multiple short sequences into a single long context window, ensuring the GPUs never waste compute cycles processing empty padding tokens. This entire infrastructure setup is designed to solve a stability versus plasticity dilemma. The model has to be plastic enough to learn highly specific routing and tool skills, but stable enough that it maintains its baseline language comprehension. Once the orchestrator is trained, it has to be evaluated. But as Goodhart's law states, when a measure becomes a target, it ceases to be a good measure. Standard benchmarks like MMLU are heavily saturated and effectively part of the training data, meaning they tell us very little about a model's actual ability to navigate novel tool environments. Instead, the orchestrator is tested against humanity's last exam, a dataset of PhD-level questions. Most language models fail these because they lack specialized domain computations. The orchestrator succeeds are to be solved. Then there is the frames benchmark, which tests multi-hop factual reasoning. When the model retrieves data, the tool might return thousands of tokens of useless noise. This benchmark specifically audits the orchestrator's attention mechanism, testing its ability to resist distractor injection and hold multiple disparate facts in its context window without losing the thread. These evaluations prove the model works inside a laboratory harness. But out in the wild, APIs change and search engines return spam. A benchmark measures peak capability with strict turn limits, whereas true production reliability requires ensuring the model doesn't enter an infinite loop that racks up a $10,000 server bill. To gauge that cost, researchers often use an accuracy per dollar metric. But a linear exchange rate between accuracy and cost is flawed. In medical diagnosis or legal analysis, 99% accuracy has massive value, while 90% accuracy carries crippling liability. Rewarding a model simply for being cheap and mediocre is dangerous in high-stakes environments. When deploying an agentic system, engineering teams face a stark choice. A single monolithic model offers high reliability for simple, low-volume tasks. A hard-coded, rule-based router offers perfect predictability for stable, narrow workflows. The reinforcement learning orchestrator sits in a different category entirely, built for high-volume, dynamic environments where task types constantly shift. This table shows the core trade-off at the heart of modern AI architecture. Using a trained orchestrator trades massive operational complexity during the back-end training phase in exchange for deep cost efficiency on the front end. Building a single massive brain to answer every question is no longer viable. The path forward lies on building a factory of specialized tools managed by a lightweight orchestrator trained exactly how to run it.